Welcome to the first presentation in Unit 6 entitled Do the Wave. It says if you saw a heat wave, would you wave back? So the learning goals for this particular presentation are that students differentiate between matter and waves, that you give an example of waves in everyday life, and that you be able to apply vocabulary terms for waves to mechanical and electromagnetic waves. So here's what we already know. We know that energy is always a conserved quantity. If you have 10 joules of energy over here, no matter what you do to it, you're going to have 10 joules of energy over here. Now that 10 joules of energy can look different. It can be heat on the left and it can be gravitational energy on the right. But no matter what you do, that energy value is going to be the same. We also know that heat can be transferred by waves, which we called infrared radiation. Okay, so you've seen that before if you've ever seen one of those infrared lamps that actually keeps food hot under a restaurant whenever they're getting ready to take it out. You also know that the electromagnetic spectrum can give you information about our universe, and that's from middle school. So, here's what we learned in the lab. We learned that waves can actually occupy the same space at the same time. If you have waves that are going towards each other, for that brief instant when they're in the same place at the same time, it's an additive effect. Okay, we call that wave superposition. We also learned several key vocabulary terms in the lab that we're going to go ahead and explore a little bit further in this presentation. And finally, we learned that the greater the energy, the higher the amplitude. So, waves are traveling energy, and that's a key thing right there. Is a lot of people think of waves as, oh, look, it's an ocean wave. Well, it's the wave is traveling in the water, or the wave is traveling in the air. But it's not a displacement, or it's a displacement of matter, but it's not matter itself. So this wave can exist independently of the water. So you can take a water wave out of the water. Okay, waves are traveling disturbances of energy, not matter. Because of that, they can occupy the same place at the same time. Matter cannot do that. Matter cannot occupy the same place at the same time because there's atoms that are in the way. Energy can, as it moves through the atoms, it can displace the atoms, it can move them up and down, but at the same time, you can have superposition. Now, what we have is a mechanical wave. Mechanical waves are things that physically disturb matter. And you see that with water. Whenever you put a drop in water, what you're doing is you're physically disturbing the water as it spreads out in a wave. The wave is the energy moving through the water that causes the ripple pattern. So other examples of mechanical waves are ocean waves like you see here. The slinky, which we did in the lab, where you kind of move the slinky up and down, or even if you kind of press the slinky in and then let it out where it kind of goes back and forth that way. That's a mechanical wave as well. Even sound waves are mechanical waves because what they do is they displace the air itself. So they make the air molecules move closer and further apart. In addition to that, you have earthquakes. Earthquakes are examples of actually two different mechanical waves. So there's lots of different examples of mechanical waves. The ones that we're going to look at in a little bit more detail are sound waves. And this is what you see actually with a sound wave. Sound waves are longitudinal, but sometimes they're called compression waves. And see what you have here is a compression. This right here is a place where the sound or the air molecules are kind of pressed together because of a sound wave. And it carries this energy that can be felt as a vibration. You can actually feel sound. Our eardrums are actually able to convert these pressure waves into an electronic signal for our brain. Humans can hear sounds that produce between 20 and 20,000 hertz, and we'll actually talk about this a little bit more later. But humans can hear 20 to 20,000 hertz. Anything that is below 20 hertz is outside the range of any human hearing, and therefore is called infrasonic. The term infra means below. Anything that's above 20,000 hertz is actually too has too high of a frequency, and we'll talk about that later. If it has too high of a frequency, we can't hear it either, and therefore it's called ultrasonic. Okay, another type of wave that we need to talk about is an electromagnetic wave. Electromagnetic waves are waves that oscillate in the electric and magnetic fields. Electric waves are kind of interesting because they oscillate up and down, but they also oscillate in the third dimension side to side, and it's kind of hard to draw the third dimension, but you have one dimension, two dimensions, and then they're moving along this axis here. So you have oscillations in two different dimensions, the electric and magnetic fields. Now a couple of examples of, not mechanical, but electromagnetic waves include radio waves, light waves, and X-rays. Now you're actually going to do a project at the end of this term in which you examine different parts of the electromagnetic spectrum in more detail. Okay, but here's an overview. Light is just a very, very small part of the electromagnetic spectrum, and you see this right here. This is the visible part of the electromagnetic spectrum when this constitutes the entire thing. So if you look how small of a fraction that is compared to everything else, the electromagnetic spectrum includes radio, microwave, infrared, visible, ultraviolet, X-rays, and gamma rays. Now when you look at all those and combine them, they make up the electromagnetic spectrum. So now we need to look a little bit into more detail of what the definitions involving waves are. Now the period is the time that it takes to reach an identical point of the wave, or how long it takes for one wave cycle to complete. Now you have two graphs right here, and you can't get period from both of them. Because, for example, this one is a time versus amplitude graph, and this is a distance versus amplitude graph. So you always have to look at a graph and say, well, what does it say? Does it say time? Does it say distance? If it says time, I can get the period. And what I do is I select identical points on the wave, like the peaks, and I say, okay, how long does it take me to go from here to here? And I would look at the graph and it would say something like this is 5 seconds and this is 7 seconds. So because of that, it would be 2 seconds that it takes me to go from this part of the wave to this part of the wave. The period is really useful, and we'll talk about why in the second presentation. Frequency is the number of cycles per second. So it's like, okay, how many of these bumps do you have in a certain amount of time? Frequency is what we talk about when you're referring to radio stations. Whenever you say 96.7 FM, the FM means times 10 to the 6th. So really what you're doing is you're telling the exact frequency that you want the radio to listen to. And finally, you can see that waves are generally expressed mathematically as a sine or a cosine graph. Okay, so what you have here is you have a sine or a cosine graph, and you can actually maneuver this wave by multiplying it by something, but you can put it in your graphing calculator and get that. So, a couple of other things of interest. The crest is the highest point of the wave. The highest point of the wave is the point of maximum amplitude. It's also considered to be the point of highest energy. The trough is the lowest point of the wave, and it is generally considered to be the point of lowest energy. So you have the trough and you have the crest. Now you also have the wavelength. The wavelength is very similar to the period. It is the distance between peaks, though, instead of the time between peaks. Generally, we're going to refer to the wavelength as this term right here. It's a Greek letter lambda. It looks kind of like an upside down Y. And this right here is going to be really important as well. So when you look at the wavelength, we're talking about the distance between those particular peaks. And finally, the media. The media is what the wave is actually traveling in. Almost all waves, all mechanical waves definitely, need something to travel in. So is the sound traveling in air? Is it traveling in water? Is it traveling in like metal or steel? So the way that this sound changes depends on what it's traveling through. Okay, wave energy. As the energy of a wave increases, its amplitude increases. So what happens is as you increase the energy of this wave, this right here, the crest gets higher and the trough gets lower. So you have these values right here increase as energy increases. Well, that can actually manifest itself depending on the wave. If it's an earthquake wave, it means the ground is going to experience more up and down motion. Okay, if it's a sound wave, the sound is going to be louder. If it's a light wave, then it's going to be brighter. So the amplitude, which is related to energy, is actually measured from this equilibrium point. The middle of these particular waves is called the equilibrium point, and the amplitude is actually from the equilibrium point to the highest point, which is also the same as the equilibrium point to the lowest point. So if you're trying to find the amplitude, realize it is not the whole thing. top to bottom. It's actually half of that. The amplitude is half the top to the bottom. So it says label the graph with the terms below. The first one is wavelength. So we're going to say, okay, wavelength is the distance between identical points on a graph. So I can say this right here is a wavelength because it's from crest to crest. Okay, then it says label the crests. So we're going to go ahead and take this first one and we're going to label that as the crest. It says label the trough, that's the lowest point. And it says measure the amplitude. And the amplitude is the distance from a crest to this equilibrium line. Okay, next it says match the vocabulary term with the definition below. It says period. Period is the time required to complete a wave. Amplitude is the maximum displacement of the wave, and the wavelength is the distance of the wave. Next it says, oh my god, I'm gonna fucking kill that cat. It says ocean waves can clearly be seen displacing water. It says how can two ocean waves occupy the same space at the same time? And the reason why is because waves are not matter. If you have two objects, say two basketballs, those two basketballs cannot occupy the same space at the same time because they're matter. The atoms of the matter themselves get in the way where you can't make that happen. However, waves are not matter. Instead, what you have are waves that are moving, and they do move the matter. But if I have two waves, they can meet at a particular point and they can occupy the same space at the same time. When they do, okay, they interfere or they have superposition. And we're going to go into more of that detail in just a minute. But it's because waves are not matter, they are energy. How could you observe an increase in amplitude for light? So remember, an increase in amplitude is if you have something that looks like this, you've got some sort of wave. An increase in amplitude actually increases the vertical displacement of the wave. So it would look something like that. Whenever you increase the amplitude of wave, you have an increase in the energy. Now, since it is visible light, it is something that you see. When you increase the energy, it means it's going to be more bright or brighter. Okay, so we've established the fact that since waves are energy, they can interfere with each other. In other words, they can occupy the same space at the same time. When you do, you get a pattern right here that we call an interference pattern. Okay, this is what happens whenever you drop two rocks in the water, so kind of next to each other. Instead of having two perfect circles, what happens is the two circles actually begin to interfere with each other. You get this strange pattern that you see here. It's kind of like a checkerboard pattern in the middle. It's called a superposition of waves. Whenever you're talking about the superposition of waves, if I have these waves, and I have wave 1, and I have wave 2, let's change color real quick, and if I have wave 2, for the brief instant where they are at the same place at the same time, they become a single wave. So instead of those two waves being independent, they become, do it as a black wave, they become a wave that looks like this. So they instantly become one wave. Now they don't stay together, they're only together for that brief instant in which they are in the same phase, or they're in the same space. The superposition of a wave can increase the amplitude. Whenever it increases the amplitude, it creates what we call a constructive interference, and that's what we'll talk about in just a second. Waves can actually decrease in amplitude, and it's what we call destructive interference. No matter what you do, superposition is additive. Okay? Now that doesn't mean that it always gets bigger. For example, if you have something that is 5 and you add -3, the resulting thing is 2. So you can add something and still have it get smaller. And then the waves continue along their original path. So constructive interference is when waves occupy the same pace at the same time, and the crest of the waves overlap and the troughs of the wave overlap. And you see that right here. We have two crests that are occupying the same place at the same time. For that brief instant, there is an additive effect to it. If this was 2 and this was 2, this would be 4. If this was 3 and this was 8, this would be 11. and then the waves continue on their original pathway and they go back down to their original value. So if this was 2 and then 2, it's still 2 and 2 again. So for that brief instant they're 4, but then they continue along their original path. Okay, the amplitude is increasing when we have constructive interference because you're making something larger than the original value. Destructive interference is when waves occupy the same space at the same time, but instead of a crest overlapping with a crest, you actually have a crest and a trough overlap, and that's what you see here. I have a crest and I have a trough. Now remember, you always add these waves together. So when they occupy the same space at the same time, if this is say 5 and this is -5 because it's the exact same value on the bottom, whenever these waves come into contact, for that brief instant, there is no wave. The wave has been destroyed. Now, the wave doesn't stay destroyed, it's only that destroyed for that brief instant. Okay, so when they go back on their original pathways, and they're back to being -5 and 5. Now, what you have for destructive interference is the amplitude has to decrease. It does not necessarily have to go to 0. For example, if you have a wave that looks like this, and you change the color and you have a smaller wave that looks like this for the line that we have, okay, you can destroy part of these waves, but the resultant wave is not going to completely cancel out. If this top one is 5 and this bottom one is -1 and this one is 1 and this one is -5, the wave is not going to be completely destroyed, but it will decrease in amplitude. It says waves can occupy the same space at the same time because they are energy, not matter. If you can see, this is a really important topic in this particular presentation. Okay, it says draw two waves that constructively interfering with one another. So constructively interfering means that you're going to have a crest overlap with a crest and a trough overlap with a trough. So we're going to go ahead and draw that out. So we have two waves. So this is an example of a crest overlapping with a crest and a trough overlapping with a trough. Okay, it says when these two waves meet at point P, what will the resultant amplitude be? So if you look, when they're going to occupy the same space at the same time, I can add the waves together. So I have A, and then I'm going to add, now this is underneath this line, so remember that it's -A. So when you add A and -A together, you get 0. In other words, this wave will be perfectly destroyed at point P. This is a student is investigating the possibility of generating true noise cancellation headphones. Explain what would be necessary to truly cancel a sound out. So if I have some sort of sound, in order to cancel out that sound, I would have to emit a sound that is the exact same as that sound, but in the opposite phase. This is called the opposite phase. And the resulting combination of these two waves would be a superposition, and it would be a straight line. Because if this is, say, 1 and this is -1, it cancels out to 0. If this is 1 and this is -1, it cancels out to 0. And so on and so on and so on. So it goes to 0, goes to 0, goes to 0. As a result of that, there is no sound wave. The sound wave has been canceled or destroyed. As a result of that, if the sound wave is destroyed, you can't hear it or detect it.